All right, guys, we're going to go back and look at our inverse trig stuff again. Let's begin this slideshow from the beginning. We covered the first couple slides in the uh, in in the series of the PowerPoint series, and we talked about how we built the inverse sine from a chunk of the sine graph running from negative pi over 2 to pi over 2. Uh, and then we flip that across to y equals x. The curvature changed as we saw here, and we could see that the inverse sine, okay, which has two different formats: the inverse sine with the raised -1, or the arc sine, live within this very small world between a domain between -1 and 1, and the range between negative pi over 2 and pi over 2. Okay, so and likewise we talked about the cosine graph again, it not being 1 to 1, uh, except if we took a small chunk of it, and we can't take the small chunk that we took of the sine from negative pi over 2 to pi over 2 because that's not 1 on 1. So we take the chunk going from 0 to pi, which is this piece of the cosine graph up there, and that's what we're going to use to build our inverse cosine on. Okay, so that being the case, our inverse cosine looks like this. It, much like the sine, is defined between the domain values of -1 to 1 and the range values between 0 and pi. Okay, now and again we looked at tangent. Tangent we saw over one cycle from negative pi over 2 to pi over 2 was 1 on 1, so we don't really have to take any restrictions other than to look at that one cycle to build our inverse tan. So again, our inverse tan is going to go with the impact of taking this one cycle of the tangent and flipping across y equals x, which is going to look like this, which is going to result in a domain which is infinite from negative to positive infinity, but a range which is bounded by asymptotes on the bottom by pi over 2 negative and on the top by pi over 2 positive. Okay, now we want to look at some computational exercises. Okay, so we're going to be asked to do kind of reverse of what we've done before. Before we had questions which were phrased the other way around. This now reads, what is the inverse sine of 1/2? Okay, so that's the same as solving this expression, this equation. Y is equal to the inverse sine of 1/2. Okay, or okay. So we recall what the graph of the inverse sine looked like. We recall that the inverse sine had a domain between -1 and 1. So we can look at that. And we also realize its range was between negative pi over 2 and pi over 2. Okay? But, okay, in a sense, we can take this and revert it back to the sine of x equaling 1/2, from which we know their familiar values are pi over 6 and 5 pi over 6. But the original questions was with the inverse sine, and the inverse sine, as we recall from our graph, is 1 to 1. So we can only take the value of the pi over 6, okay, because because this value of 5 pi over 6 is outside of our range of pi over 2 to the negative pi over 2. So that's the things we got to bear in mind, okay? Uh, so the 5 pi over 6 is excluded because it's out of the range of the graphs of um, the inverse sine. And so ultimately, the inverse sine of 1/2 is simply the single value solution of, okay, pi over 6. Again, here's our graph, which kind of explains it. Okay, so if we're looking at 1/2, uh, the inverse sine, here's our inverse sine. We evaluate inverse sine of 1/2. We're only going to get back one value. That's going to be the pi over 6. Okay, we were going to give the inverse sine of -1/2. Then, of course, we come up with this value over here. Okay, negative pi over 6. Okay, all right. So let's look at some other examples. The arc cosine of 2 pi. Well, that's the same as the inverse cosine of 2 pi. Okay, but remember, from the cosine, the inverse cosine was only we're only allowed to take a chunk we're only allowed to define the domain of the inverse cosine between -1 and 1. This is well outside of that range, so therefore there's no accepted value. How about the inverse tan of root 3 over 3? Well, root 3 over 3 should be a familiar stop for us on the unit circle with the tangent, which should ring up as a pi over 6 equivalent, okay? Uh, the equivalent expression now is only one solution, but the equivalent expression is to say that's the inverse, that's the tan of x equaling root 3 over 3. But again, remember, we're only going over the first cycle because that's the limitations we put on the inverse. That's the limitations we put on the tangent when taking its inverse. So we're only taking the one solution pi over 6. Okay? We're going to look at solving some equations which we which might call on us to use the calculator as such, okay? So the sine of x equaling 1/4, all right? Well, certainly there is a solution to that. So here's the sine of x, here's 1/4. Certainly we have a solution. In fact, we have two solutions per cycle. They're not well-known values for us, okay? But they certainly agree that there is a solution. So we're going to, for the first time here, use our calculator to find what this is, okay? But we should agree to the following. Whatever this solution is, okay, whatever the solution is, A, the solution over here is going to be pi short of A, okay? Pi short of A. So this is A, and this is pi minus A, okay? So I'm going to my calculator. I'm going to set my calculator to the radian mode, okay? And I'm going to ask for the inverse sine of 1/4, 0.25. And this says it is 0.25, okay? But now my two hits where that's going to happen are going to be that 0.25 and pi minus that value, which figures numerically to be 2.88, okay? Um, a similar type deal. Solve the equation using inverse trig. Cosine of theta equals 3/4. Yes, certainly there is a solution for cosine equaling 3/4. But in order to find that solution, since it's not a familiar stop on the unit circle for us, we're going to say, what is the inverse cosine of 3/4? So we're going to ask our calculator the inverse cosine of 3/4. It's going to tell us it is 0.72. Again, we have to be in radian mode, okay? So that's telling us that that is, okay, the radian value, okay, 0.72, when the cosine is equal to 3/4. When will the cosine equal 3/4 again? Well, it will be in that value, that angle value less 2 pi, less taken from 2 pi. So 2 pi minus that would be the next value where that hits, okay? So using the cosine inverse will give us the decimal equivalent in radians, but then realizing that the cosine is both positive and, the cosine is positive in both the first and the fourth quadrant, okay? And then if whatever this value is, the fourth quadrant reference would be 2 pi minus that, okay? Um, so we have but one inverse trig identity that pops up, okay? So we've got our familiar 3, 4, 5 triangle here, okay? Um, and of course, we should agree that the sine of alpha is opposite over adjacent, opposite over hypotenuse. That's 3 over 5. Cosine is, okay, I'm looking at, cosine of alpha is 3 over 5. And the cosine of beta is 3 over 5, okay? Then therefore, okay, um, we can conclude that alpha is the inverse sine of 3/5 and beta is the inverse sine of um, the inverse cosine of 3/5, okay? Now, of course, we realize that this being a right triangle, the sum of alpha and beta is 90 degrees or pi over 2, okay? So therefore, we come to conclude that the sine of the inverse sine of 3/5 plus the inverse cosine of 3/5 is pi over 2. Or in general, we're going to state that the inverse sine of an angle plus the inverse cosine of an angle is always equal to pi over 2. Okay? Um, Evaluate some of these expressions. The sine of the inverse sine, that should be -1, sine of the inverse sine of 1/2. We can move from the inside out, okay? So if we take the inverse, if we agree that the inverse sine of 1/2 is pi over 6, then this is simply saying what is the sine of pi over 6? Okay, and the sine of pi over 6 is 1/2, okay? So, so the sine of the inverse sine of 1/2 is equal to 1/2. Um, that shouldn't come as a surprise because we're dealing with inverse functions.